Today we're going to learn about modeling with variables, specifically with two variables and two or more variables. When we talk about modeling with variables, we're describing real world situations with math. So a variable is just something that can change, like time, cost, distance, or temperature. With one variable, usually we're tracking how one thing changes. Like, for example, how distance changes over time. When we have two variables, we start looking at relationships between quantities. An example of that would be how the price of something depends on how many items that you buy. One variable is depending on the other. When we move two or more variables, the model becomes more realistic. Real world situations, they rarely depend on just one thing. So, for example, profit might depend on price, cost, and quantity all at the same time. So the goal of modeling is to look at a situation, define the variables clearly, and then build an equation that shows how they're connected. Once we have that equation, we can solve for any variable that we want to find the value of, and then we can make predictions or decisions based on that. So to start with, we're going to look at modeling with two variables. These first questions are asking us to examine graphs, and we want to decide if there's anything that needs to be changed on the graph. So here we have a quadratic function that's graphed here. It says Jasmine modeled the relationship between the altitude uh, of a tree, A, in meters above sea level, and the tree's growth rate, R, in millimeters per year. And then it gives us this equation. And she wants to graph the relationship for these altitudes between 0 and 9,000 meters. And this is her work here. And we're looking for if there are any mistakes on the graph. So let's take a look at all the multiple choice options here. Um, So it says inappropriate scale for x-axis, inappropriate scale for y-axis, wrong or missing labels for the both of the axis, or there's no mistake at all. So looking at what she wanted to graph here, it says that the altitudes are between 0 and 9,000 meters. And it also says that the growth rate is R, and it says R equals. So this would be y equals. So we can say R is y, or the growth rate. And if we check our y-axis, it looks like we have growth rate on our y-axis. So that looks correct for the label for the y-axis. So we can cross that out. I'm just going to put an X there for missing label for y-axis because that's not correct. We do have a label for the y-axis. For the x-axis, altitude, looks like they give us altitude, and it does go to 9,000. Here's the 9,000 mark. And so it looks like we can cross that out. We do have an appropriate label for the x-axis, and we also have an appropriate scale for the x-axis because that goes to 9,000. The scale for the y-axis, it looks like everything is included in this graph here. We could plug in points for A and figure out where all those are on the graph, but just looking at the graph, nothing's gotten cut off. It's an appropriate scale. If the graph was smaller and it was like that, and there's a bunch of extra room at the top, then maybe we could argue that it's not a correct scale, but it looks basically to scale. So in this case, there's no mistakes on this graph. But I think that's a good example to start with so that we can see uh, which what sorts of qualities that we're looking for um, um, in terms of the x-axis and the y-axis. All right, the next example, Lauren modeled the relationship between the number of days that had passed since she planted a cactus and its height in centimeters as h equals 10 plus 2t. She wanted to create a graph to show the the cactus's growth in the first month, and here's her work. And we're looking for any mistakes that she made. So immediately what I can see on this is that there is no there's no label on the y-axis. So we can say wrong or missing label for y-axis. There's a missing label for that. Um, Also, it says that this is for the first month. And so that goes to 30 days if this is going up by fives. So that looks right. But if so that's the appropriate scale for the x-axis. Oops, it's appropriate. So that's not an answer. So we do have the correct scale for the x-axis, and we also have the correct label for the x-axis, so we can cross that out as well. The scale for the y-axis, though, this needs to be updated as well because that's not the right scale. Our graph is getting cut off at 10 days. So if these numbers went higher, we would be able to figure out what those are for when x equals 30. And that's the data that we need to find is for all the way through 30 days. So it's an inappropriate scale for the y-axis also. Okay, let's look at another one. This one looks like an exponential formula. Um, and this person invests $400 in a savings account that earns 5% interest each year. T is time, B is the account balance, and this would be y equals 400 times 1.05 to the x if you wanted to write them in terms of y and x. So now we can check is that correct for the y-axis? Does y equal the balance? It looks like yes. And it looks like x does equal time. So we have the right labels for the x and the y-axis. So we can cross this out because this has the wrong label. It is the right label, so we can say those are not right because we do have the right label. Okay, so now let's take a look at how far we want to go and check our scale for these. So it says they wanted to create a graph to show the balance over the first 10 years. This goes to year 8. And if we stopped at year 8, this might be acceptable because we can see what the value is at year 8. But if we go to 9 and 10, we don't know what that value is. Um, we can plug in some values in the equation, but it doesn't show us properly on the graph. So we would say there's an inappropriate scale for the x-axis, and there's also an inappropriate scale for the y-axis. So at first glance, it looks like the y is okay because everything fits on there, but it doesn't because if we have something that goes out to 10, then on the y-axis, it's going to get cut off as well. So both the x and the y-axis have an inappropriate scale. All right, so we looked a little bit at some graphs. Now let's take a look at equations and inequalities word problems. This first problem is it's an exponential problem, and we have to know about exponential equations and how they're formed. So the basic form of an exponential equation is y equals ab to the x. And we can also write that f of x is ab to the x. A is our starting amount. And B is usually written as a percentage where it is either 100% plus whatever the percent is as a decimal or minus whatever the percent is as a decimal. And we write that as, instead of percent, we write B is 1 plus or minus, and we write that as R. Sometimes you'll see that as R. So if B is 1 plus the percent, we call that growth. If B is 1 minus the percent, that's decay. And when we're talking about anything to do with a total amount in terms of money and finances, we can rewrite this. We can rewrite this equation as A is the final total amount is equal to P, the principal amount or the original invested, times 1 plus or minus R, which is our percent growth or decay rate, to the power of T. All right, so A is the final amount. P is the starting amount. And we also call that the principal. R is our percent, and then T is time. All right. So now let's take a look at our word problem. It says Samantha opened a savings account. She deposited $8,192. The account earns 10% interest annually. She makes no more deposits and does not withdraw any money. After T years, we don't know how many years that's been, she has $25,710 in this account. So she's not adding any extra money. She's just earning the 10% interest, and that's 25,000 is her final amount. And we want to write an equation that shows the situation. So it doesn't want us to solve for how long that it took. We could do that, but it just wants us to write the equation for this. So at the end, her final amount is $25,710. Her principal starting amount is $8,192 times 1. This one's going to be plus because she's earning 10% interest. So plus 0.10 or just 0.1. And then to the power of T. And then you can simplify this as 1.1 to the power of T. And that's all it wants us to do for this equation. Now you can solve this with logs if you remember how to do logs, but we're not going to go that far in this example. Okay, this next example is we need to use the distance formula for this next example. So these two people are running a race. And let me just write the formula that we're going to need for this to start with. Distance equals rate times time. So the Jacksons and the Simpsons were racing, and the race is 240 kilometers long. In their race to the finish, the Jacksons took off traveling at an average speed of v kilometers per hour. The Simpsons' start was delayed by an hour. When they eventually took off, they traveled at an average speed that was 40 kilometers faster than the Jacksons' speed, excuse me. Sadly for them, that didn't help and the Jacksons won. Write an inequality in terms of V that shows the situation. So our last example had an equals. This example is going to have a less than or a greater than symbol. So the Jacksons won. So the Jacksons, whatever their time is going to be less than the Simpsons. So that's our first thing we can do to model this inequality. And we're comparing their time in hours to the other people's time in hours. So we're just comparing time and time. But now we need to figure out how can we represent the Jacksons' time in hours? And then how can we represent the Simpsons' time in hours? So for the Jacksons' time, it says that the race was 240 kilometers long. If they're running a race, then the distance for both of those both the Jacksons and the Simpsons has to be 240. So we're right. D is 240. Now for the rate for the Jacksons, um, the rate, it just says that the Jacksons were going V kilometers per hour. So that was their rate. And then we don't know what the time is. And so we want to solve for the time or the hours. So we're going to divide by V on both sides. And we get that the Jackson's time is 240 divided by V. Now for the Simpsons time, it says they traveled at an average speed that was 40 kilometers faster than the Jacksons. So their rate is going to be the Jackson's rate plus 40. And we're going to put that in parentheses because we're substituting that for what R is. And then times the, not just the time, but there's a second part to this. And it says that the Simpsons start was delayed by an hour. So their time wasn't just the same time, it was the time minus 1 hour because it was delayed by 1 hour. Now you might be tempted to do the distributive property with this. We're just solving for what t is, and we already have 1t there. So instead of multiplying this out, we're going to divide by v plus 40 on both sides. And that crosses that out. So now we have t minus 1 equals 240 over v plus 40. And we're just going to add that 1 to both sides, and we get t equals 240 over v plus 40 plus 1 for the Simpsons time. And now it just wants us to write the inequality. We have that the Jacksons' time was less than the Simpsons. So we're just going to write that this t, we'll say that's t sub j for Jacksons and t sub s for Simpsons. So we would just write like t sub j is less than t sub s. And we're just going to plug in those values. So 240 over v is less than 240 over v plus 40 plus 1. And that's our final answer for this one. So it just wants us to figure out what these variables are and then write it if it says in terms of a variable. In this case, we wanted to write everything so that there was only v's left. All right. This next problem is asking us to write an equation in terms of x. We need to know the area formula for this. Area is equal to the length times the width. So we have a picture and it's in this frame, and when we put it in the frame, it creates a border of x around the picture. So all of this is the border. And I'm actually going to erase that so that we can see these x's a little bit easier. So all that's the border. The picture is 4 by 6. And it says the area of the entire frame, including where the picture is placed, is equal to 55.25 square inches. Okay, so we know that for area is 55.25, and that equals the length. The length is from here. Let me write it from corner to corner instead. From here to here is the length. So we know that from here to here is 6. If we add this part, that's 6 plus x. And then if we add this other part, this is also x. So the length is 6 plus 2x. And then we're going to do a similar thing for the width. So the width is 4 from here to here. And then if we want to know from there to there, that's the width. And measure that. All right, what the length was there. The width is also, that's x, and that's x. So the width is 4 plus 2x. And then we can multiply this. using the distributive property, we would get 24 plus 12x plus 8x plus 4x squared, 24x, or 24, excuse me, plus 20x plus 4x squared. And then we could set this equal to 0 and use the quadratic formula or attempt to factor this to solve for what x actually is. But it doesn't want us to do that. It just says write an equation in terms of x. So we could just say that's our final answer. In fact, if you wrote this as your final answer, I believe that would accept the answer as well. I think that would be appropriate if you just went to there and were able to define what the variables are. All right, let's look at one more inequality one. I thought this one was a little bit tougher than the other ones. On her way home from the laboratory, Duru realized that she left a test tube containing 50,000 bacteria in a lab. Every minute that passes, one third the total number of bacteria duplicate. If the number of bacteria reaches 100,000, the test tube will explode. So naturally, she turned around and rushed back to the lab. It took her T minutes to return to the lab, and she found the test tube intact, so it didn't explode. We want to write an inequality in terms of T that models the situation. Okay, so the bacteria have to be less than 100,000. So for our first step, we're just going to say 100,000 bacteria. So just as a quick reminder, you can read an inequality just like you normally read from left to right, like 100,000 is greater than the bacteria, or you can read from right to left, the bacteria is less than 100,000. Okay, so that's our first part of this. Now this is growing exponentially. It says that one third the total number of bacteria duplicates. So the exponential formula for the bacteria is going to be, we're going to say A for our total has to be less than, and now we're going to write what's happening with the bacteria in terms of exponential growth. So we started with 50,000 bacteria. Let me write this up here. A is equal to P times 1 plus or minus R to the T. We're using that same formula, except instead of equals, we're writing a greater than. Because this bacteria, all of what this bacteria is, has to be less than the final amount of 100,000. So our starting amount is 50,000 times 1 plus our rate in this case is 1/3 or 0.33 repeating. I'm going to write just 1/3 though to make sure it's exact. And then that's going to be to the power of t. And then we just simplify this. So A is less than 50,000 to the 4/3, or excuse me, times 4/3 to the t. And I should have written our 100,000 as our final amount. Okay, so that's the inequality that models this situation. All right, next we're going to look at modeling with multiple variables. So we're going to use some of these same equations that we've used previously, except now we have more than one variable to be dealing with. So this first one says Alana went for a run. She ran d kilometers at an average speed of v kilometers per hour. Then she walked to cool down for 0.25 hours. The total duration of the trip was t hours. Write an equation that relates d, v, and t. So in this case, we don't have to write D equals or V equals or T equals. We just have to choose how we want to write this equation. We just have to make sure also that all three of these letters are in our equation. So we're going to use the equation D equals RT. And in this case, instead of R, we're going to write D equals VT. So distance is rate times time. The rate is the velocity, V. So V is the running speed, T is the time, and D is the distance. All right, so first we're going to find the total running time. So the total running time is D equals VT of the time that she spent running. And if we want to write the time now, we're going to solve for T or time of the running time. So T of the running time is equal to D over V, and that's in hours. You don't have to write the hours. I'm just writing that there to show you that that's equal to time. Okay. And then she spent 0.25 hours walking. So now if we want to write the total, the time total is equal to the time that she spent running plus the time that she spent walking. So the total time equals D over V plus her time that she spent walking is 0.25. Now, the key takeaway from this is that we're writing everything in terms of time. Time equals time plus time. If you try to write time equals time plus distance or some other variable, then the equation won't hold true. So just make sure that when you're finding the total of something, that you are using the correct units to find that total. All right, let's take a look at another one. The company uses 3 trucks to deliver a total of T liters of cement. Each truck can transport X liters of cement per trip and makes a total of Y trips. Write an equation that relates T, X, and Y. Okay, so let's figure out first how we can write what one truck would be in terms of uh, X and Y. So for one truck, that is X liters per trip. And it makes a total of Y trips. So one truck is carrying liters of cement. So now we have to ask ourselves, what do we do? What operation do we do with Y to make the trip cancel out? Well, there's Y trips. And so if we multiply, then the trip and the trip cancels out. So now one truck is equal to X, Y. And there's just liters. So remember, the truck is carrying liters of cement. And so now we have liters equals liters. This is just for one truck. It wants to know what is 3 trucks. Okay, now for 3 trucks is not equal to 3t, it's still going to be just t equals 3 times xy liters for 3 trucks. So that's going to be our final answer for this one. We're multiplying the total liters by 3. If we wrote 3t, we would be dividing the total liters by 3, and we don't want to do that. We have 1 truck and we're multiplying by 3 to get what 3 trucks is. All right. I like this next example. I think this next example illustrates very well how we can use table data to write equations for multiple variables. So this person is making a salad with these different ingredients, and the table tells us the cost per kilogram and the amount that this person is using for their salad. So the total amount is C. Um, so we're going to find an equation that equals C, which is in dollars. So we want to convert everything to dollars. So let's first figure out the dollars of tomatoes. That's our first food item on there. So for dollars of tomatoes, if we want to take this information and figure out how many dollars that we spent on tomatoes, we would say $3. Well, let me start with the amount. There's 0.3 kilograms times $3.30 per kilogram of tomatoes. Now we can cross out kilograms and kilograms, and that just leaves us with dollars. And so when we do the math for that, we get 99 cents or 0.99. So all we're trying to do again is we're trying to figure out what operation do we need to do in order to get rid of the kilograms and convert our answer just to dollars. Okay, let's do the next one for dollars of cucumbers. We have Y kilograms of cucumbers times X dollars per kilogram. Kilograms and kilograms is going to cancel out, and that gives us XY dollars. We don't know how much that is, but that's okay. We just want everything in terms of dollars for all 3 of these food items. Okay, and then for carrots, we have 0.2 kilograms. I think you might be seeing the pattern now, times Z dollars per kilogram. Cross out the kilograms, those end up canceling out. And now we have 0.2 Z dollars. We're going to add all these together for the total cost. So C is the total of all the dollar amounts of these food items. So we're going to write, and we don't have to write the dollars, so I'm just going to take the dollar symbol out. So it's 0.99 plus XY plus 0.2 Z is what C equals. Remember to write the C when you're putting your answer in for these, or to write the equal sign. If you just write the expression, you won't get credit for the problem. All right, let's look at one more with the multiple variables. I thought this was a tougher example. Each Christmas elf makes X toys in an hour. N elves work for T hours to produce 1,000 toys. Write an equation that relates X, N, and T. All right, so we want to we want to define toys for each variable. So we have 1,000 toys. So we know that this is going to be 1,000 equals something in terms of x, n, and t. So the first part is defining what these variables are. We have t hours, we have n elves. Those are fine, but the part that I think is tough is it says each elf makes X toys in an hour. So when we're defining X, we can say X toys. If you just write X toys per hour, you might get stuck on this problem. It's X toys per hour per elf. And if we rewrite that and we have a complex fraction, if we rewrite that, that's X toys per hour. And then I'm just going to say times 1 over elf. That's the same thing there. So now we can rewrite this as X toys per hour elf. And you might be wondering why we had to make this conversion. The reason is we want to find a way to cancel, like with the previous problems, to just be left with toys. So we want toys equals toys for the X, toys for N, and toys for T. So we want all of our units to cancel out in a way that we're just left with the toys. So here's what our X variable is going to be. So far now we have 1,000 equals X toys per hour elf, or per elf if you want to say it like that. Now we have to figure out, well, what can we multiply to get rid of hours and elves? Well, if we just multiply by n elves, that cancels out the elf part. And then if we multiply by t hours, that cancels out the hours part. And now we're just left with toys. 1,000 toys equals this amount of toys. So 1,000 equals x and t. So when you're doing these problems, ask yourself if it's possible to multiply to cancel out units that we want to get rid of so that we can write an equation that is a true statement where we have the same units on the left side of the equation as the right side of the equation. That's I would say the main takeaway for all of these problems. All right, let's keep going here. We've got just a few problems left. The next part is interpreting expressions with multiple variables. And I think these aren't too bad. These are literal equations. You can sometimes just plug in a number for the variables and then see if these answer options are either true or false. So we have this equation or this expression a plus 2 over b. And it wants to know which of these actions will cause the expression's value to increase. So when we have these things happening, what's going to make this go up? And you might be able to intuitively figure this out without writing down much math on your own, but I'm going to show you a way that you can solve this by just letting a and b equal some amount. So we're going to say let a equal 5 and let b equal 3. These are just random numbers that I picked. You can choose any number that you want. It's totally okay. But now we're going to look at what would that make our original equation then. So our original equation, if we plug those in, that would become 5 plus 2/3. or 5 2/3 as a mixed number. So now we're going to look at what happens if we make these changes. So let's look at A. It says keeping A constant and increasing B. So if we keep A constant, that's 5 plus 2 over. Now, if we increase B, we can choose any number really. Um, I'm just gonna make it 5. So it's as long as it's bigger than 3, that's fine. So now we have 5 2/5. Now we have to check which one is bigger. Is this bigger than this? Well, you can always check on your calculator if you need to. 2/3 is 0.6 repeating. 2/5 is 0.4. So A is less than the original. So I'm just going to write A is less than the original. I'm going to say just OR, I guess, for the original. So that's not true. For B, if we keep A constant, we get 5 plus. If we decrease B, let's say B is going to be 2, then that's 2 over 2, which is equal to 5 plus 1, which is equal to 6. And so in this case now, A is greater than our original. And so that is one of our answers. Now if we try C, we're going to increase A. I'm just going to make A equal 10. And then it says keep B the same. Well, that's 10 2/3. And so that means that A is bigger than our original. And that one's correct. And then finally for D, if we decrease A and keep B constant, now let's let A be 1. I'm just choosing 1. I'm just choosing something that's lower than 5. Plus keeping B constant, 2 over 3. That's 1 2/3. So that's going to be A is less than our original, and that does not cause it to increase. So B and C are our final answers for this one. Okay, got a couple more to go here. Um, this is a literal equation that you typically see in geometry. I think we're going to look at another one that we see in physics as well in a little bit here. But this is one we see in geometry. So Danny's measuring two pyramids whose bases are squares. We're given the height h and the volume v of the first pyramid. Danny uses this formula to compute the side length a to be 5 meters. So I'm going to write what Danny found for our given or for his given formula. He found that a was 5, so we're going to write 5 equals the square root of 3v over h. And if we rewrite that, that's the same thing as square root of 3v over square root of h. 5 equals square root of 3v over square root of h. Okay, for our new formula, it says the second pyramid has the same volume, so v stays the same, but it has 4 times the height. And now it's saying, what is the side length of its base? So the base's side length is a. So for our new formula, we want to find what a is. So a, we don't know what that is, so make sure not to write 5 for that. So a is equal to the square root of 3v over 4h. And we can also write this separately as square root of 3v over square root of 4h. So a is equal to, if we simplify this, a is equal to square root of 4 is 2 times the square root of h. All right. And now if we write this as a equal to, instead of the 2 on the denominator, we can separate this again as 1/2 times square root of 3v over square root of h. And the reason that I did that is because now we have this original uh, part of our equation from the given equation. So now this is A is equal to 1/2 times, we know that that is equal to 5. And so A is equal to 5 over 2. And so it's just saying, what is the new A going to be? Well, it's going to be 5 over 2 meters. So trying to change these equations algebraically so that we get some uh, parts of the equation that match with our original equation can help us to solve these uh, literal equations algebraically. All right, and here's our last one. This is a similar problem. Hazel is measuring two prisms whose bases are squares. We're given the volume and the base's side length A of the first prism, and Hazel uses the formula H equals V over A squared, and she computes the height to be 10 centimeters. So Hazel's initial formula, or her given formula, is 10 equals V over A squared. So that's her initial formula. The new formula, the new formula is 5 times the volume. So the new formula, we don't know what H is, but we do know that now it's 5V over A squared. And we can rewrite this now as a multiplication problem as 5 times V over A squared. And if we look at our given information, V over A squared is equal to 10. And so the new height is going to be 50. Okay, so that is everything on modeling with variables. As you can see, we can model exponentially with graphs. We can model with tables, and we can model with equations.